This is our video about basic acid-base titrations. Now there's a lot of reasons why titrations are useful. We can use titrations to find the Ka or the Kb of an acid or a base, and that could be where the Kas and the Kbs that we look up on charts come from. We can also use titrations to standardize a solution if we want to know the concentration very accurately, like we do in Chem 5. We can also use titrations to determine the molar weight, the molecular weight of an acid or a base. And that's helpful because if we have that molecular weight and we know the empirical formula by something like a combustion reaction, we can put those two pieces of information together, the molecular weight and empirical formula, to come together to find the molecular formula of an acid. So titrations can be used for a lot of different things in chemistry. And by studying titrations and knowing what two things we're titrating, so if it's a strong acid, strong base, weak acid, strong base, weak base, strong acid, each one of those different types of titrations has different reactions going on at different times during the titration. And so this lecture is going to cover titration curves and the calculations that you can do at each point along the titration. Now, one application that might not have come up in general chemistry, but it does kind of pertain to analytical chemistry, is studying the pKa of weak acids by looking at their titration curves. Amino acids are weak acids, and their pKa's change due to the environment that they're in. So we say that the environment significantly perturbs a pKa value. That just means it changes it. So by looking at a titration curve and using that titration curve to calculate the pKa, we can tell some about the environment that an amino acid would be in. Now, this is particularly important in things like medicine and medicinal chemistry because how a molecule, like an amino acid, reacts to its environment helps us predict how easily it'll cross a cell membrane. And if you're studying something like drug delivery, you're really concerned with getting molecules across a cell membrane so that they can be delivered to the cell. So let's look at titration curves and different types of titrations and find out what kind of information we can tell along each point of the curve. Now remember, a titration curve is a plot of pH versus the amount of added titrant. So usually it is a plot of pH versus titrant added. And we're using that vague term there because the titrant added could be an acid or a base, depending on what type of titration you're doing. On a titration curve, there are inflection points. So where the slope is changing the most, so like here, that would be what we call the equivalence point of the titration. Now there's all kinds of titrations that you can do, but we're going to concentrate on first talking about strong acid, strong base. Then we're going to talk about doing a weak acid with a strong base, then a strong acid with a weak base. And we'll cover polyprotic acids later on. This is an example titration curve where we start off with an acid and we're adding some sodium hydroxide, which is a strong base. So you can see in how the pH goes up as we add the sodium hydroxide. That makes sense since sodium hydroxide is a strong base and the pH should increase to more basic pHs. There's a couple of places we're going to kind of concentrate on. We'll talk about the reason why these are so important, but we're always going to talk about kind of the beginning when the pH is just based on what's in your titration flask and you haven't added any titrant yet. We're going to talk about the equivalence point, which would be the point of steepest slope right here, and we're going to talk about the halfway point between those. We're also going to talk about somewhere up here after the titration has gone past the equivalence point. So we'll talk about how to find the pH in the beginning, halfway, at the equivalence point, and then somewhere after the equivalence point. Now, a typical question would be something like, you're given the acid or the base and what you're titrating it with. What is the pH at the equivalence point? or after a certain amount of titrant has happened. So we're going to use a titration curve to figure out what place in the curve we're at, and then kind of use the appropriate calculation to find the pH. The first titration that we're going to talk about is a strong base and a strong acid. So this is your typical acid-base titration that you would have done in general chemistry. They're pretty straightforward because it's just stoichiometry. There isn't any equilibrium really that happens with strong acids and strong bases. Everything goes to completion. Now, typically when we're doing strong acid, strong base titrations, we have an acid of unknown concentration. So we know what the identity of the acid is, but it's unknown concentration, and we titrate it by adding a base where we do know the concentration. You can flip-flop those, put the base in the titration flask and the hydrochloric acid or the acid in the burette, but usually it's the base in the burette. All of our strong acids are monoprotic acids, which means that they're going to react in a 1-to-1 ratio between the base and the acid. And that's because the real reaction, the net ionic equation here, is really the hydroxide from the base and the hydrogen from the acid reacting to make water. So those always react in a 1-to-1 ratio. As we do the titration, we measure the pH and the amount of base, and we get a titration curve. So strong acid-base titration curves have a very strong inflection point, and it's easy to find where that equivalence point would be. And so for a strong acid, strong base, the equivalence point is going to have a pH of 7. And the reason why that's true is because at the equivalence point, you've put the hydroxide and hydrogen ions in a 1-to-1 ratio with each other. They've reacted to make water. There's none of this left. There's only water. And water dissociates to make hydrogen and hydroxide ions, but only to a very small extent. The Kw there is 1 times 10 to the negative 14. So in pure water, we talked about how this is 1 times 10 to the negative 7, 1 times 10 to the negative 7, and 1 times 10 to the negative 7 hydrogen ions is what we say is a pH of 7. So pure water has a pH of 7. Pure water is the product of a strong acid, strong base titration. So the equivalence point is easy to find the pH for in a strong acid and a strong base, but there are other points in the titration curve. So let's just start at the beginning. Before we've added any base, we just have acid in the titration flask. And so the pH is going to be based just on that acid. Because it's a strong acid, we know that the concentration of the acid is equal to the concentration of the hydrogen ions. That's because strong acids totally dissociate. So we can say that the concentration of hydrogen ions is just the concentration of acid, and that's helpful because pH is equal to the negative log of that hydrogen ion concentration. So we can use that to easily calculate the pH at the very beginning before the titration has even started. Now, if we're continuing along this titration, after we've started the titration, we've added some sodium hydroxide. So that is before the equivalence point. Before the equivalence point, there's excess hydrogen ions. We just need to take into account how much of the hydrogen ions have been used up, neutralized by that base that we've added, but then we can use the rest of the hydrogen ions to calculate the pH. And then we get to the equivalence point where the hydrogen ions and hydroxides have neutralized each other, and we said that the pH is going to be 7 there for a strong acid, strong base. And then after the equivalence point, there is excess hydroxide. So the pH is going to be based on the POH, which is the negative log of the hydroxide ion concentration. Now, a little detail here. Technically, when we're trying to calculate the pH after we've added some acid or base, that problem really involves 2 steps. First, we would do a little stoichiometry calculation to figure out how much of the acid and base have reacted with each other. And then we would use the amounts that we had found that were left over and do an equilibrium calculation, so an ice table, to figure out what the equilibrium concentrations were. But for strong acids and strong bases where the K is really high, we basically assume that everything goes to completion and this part of that calculation really isn't important. So for strong acids and strong bases, we can skip that calculation, but when we start doing weak acids and weak bases, we'll have to go through and we'll have to add that part of our calculation to our pH calculations. So let's do an example. We're going to titrate 50 milliliters of a 0.05 nitric acid solution with 0.1 molar KOH. That's a strong acid and a strong base. In this problem, we're going to calculate the pH at each one of these points. And we know how to calculate the pH at each one of the points as long as we can identify what these volumes mean in terms of where they are in the titration curve. So what I mean by that is 15 milliliters of this KOH, is that before the equivalence point, at the equivalence point, or after the equivalence point? And so basically for each one of these volumes, we need to figure out which area of the titration curve it's in so we can figure out what kind of calculation we need to do for the pH. So the really big point that's easy to calculate is where the equivalence, how much volume would be at the equivalence point. So I'm going to calculate how many milliliters of KOH I would need to react with my starting amount of acid. All right, so I have my volume of acid, and it's 0.0500 molarity. They react in a 1 mole to 1 mole ratio. And my KOH is 0.1 molarity for 1,000 milliliters. So when I did that calculation, I found that the equivalence point should be 25 milliliters, and that is point C here. So this is the equivalence point. Now again, why we're doing this calculation is because we're trying to minimize the amount of calculations that we need to do overall, and we know that at the equivalence point, the pH is equal to 7 for a strong acid, strong base titration curve. So just by doing some simple stoichiometry, we've kind of knocked out one of our pH calculations. All right. Now, if 25 milliliters is the equivalence point, then that means that this is after the equivalence point. And part B is before the equivalence point. And A is at the very beginning. So there is no base here, there's only acid. And so the pH is just going to be based on that acid concentration. So let's go through each of the calculations. I've just put points A and points B here. For point A, that is just the nitric acid concentration. And since we know that it's a strong acid, the hydrogen ion concentration is going to be equal to the concentration of that strong acid. And so the pH is just going to be the negative log of 0.500. And so that's going to be a pH of 1.300. All right, so we got part A done. Part B is when we have our acid in the titration flask and we've added so much 15 milliliters of the potassium hydroxide, we need to figure out how much this potassium hydroxide took away from the nitric acid. So we're going to use stoichiometry to do that. So I'm going to calculate how many moles of the acid have been used by this potassium hydroxide, how many have been neutralized. So I'm going to use my molarity of the KOH. They react in a 1 mole to 1 mole ratio. And so I calculated that 0.0015 moles of the HNO3 was used. Now I just have to subtract that from the moles that I started with. So to calculate the moles I started with, like this, and that's equal to 0.0025. So that's what I started with, and this is used. So the HNO3 left over is going to be 0.0025 minus what was neutralized by the base. But I need molarity, so molarity is going to be moles divided by volume. I have my moles, but my volume is going to be my 50 milliliters that I started with plus the 15 milliliters of base. And so that volume is 0.065 liters, which means the molarity is 0.01538. Now we can calculate the pH. The pH is the negative log of that concentration. And that's 1.81. Now just overall, it makes sense that the pH is going up because we are adding a strong base. So we've gotten our first 2 points. Let's go on to the second 2 points. The third point is what we called the equivalence point. So we had figured that out. And we know that the equivalence point is going to have a pH of 7. All right, so done. The fourth point is where we've added an excess of potassium hydroxide. So all of our nitric acid will have been neutralized and we'll have an excess of the potassium hydroxide left over. So this calculation is going to be very similar to what we did in step B, where our pH was based on an excess of hydrogen ions. Here it's just going to be based on an excess of hydroxide ions. So we need to figure out how much excess of hydroxide we have, and that means subtracting out what was neutralized by our acid. So first we're going to calculate how many moles of the KOH we had. And that's 0.0035 moles of KOH. So now we have to calculate how much acid we have in there that would neutralize some of that KOH. We actually did that calculation back in part B. We found that 50 milliliters of a 0.05 molar solution was equal to 0.0025 moles of nitric acid. So when you do the subtraction there, you get 0.0010 moles of KOH was left over. And we can use that concentration to find the pOH. The pOH is the negative log of that hydroxide ion concentration. And that's going to come out to be 3. And we know that the pH and the pOH always add up to be 14. So 14 minus 3 is going to be the pH. So pH equals 11. Now if we go back and put in this information, I just kind of wanted to make sense. In the very beginning, we figured out that the pH was equal to 1.3. Then it went up to 1.81. And then it was a pH of 7 at the equivalence point, and then at the very end, the pH was equal to 11. And that makes sense for a strong acid, strong base titration curve, because it starts off kind of slowly moving, then it makes a big jump to 7 at the equivalence point, and then it starts to flatten out again and stop changing quite as much. So let's compare that to what it looks like for a strong base plus a weak acid. I'm just going to use HF as an example. Now we know that weak acids have lower Kas and higher pKas than strong acids, and that's going to have two effects on our titration curve. First of all, it means that the titration curve will be different and the equivalence point will not be a pH of 7. It also means that this area down here is a little bit more of a curve. So when we blow this up and we look a little bit more closely, we can see that the titration curve does look a little bit different than a strong acid and a strong base. Both of them start at acidic pHs, so both of them start at acidic pHs down here. But as we start to add base, the weak acid changes faster than the strong acid. And at the equivalence point is going to be higher than pH 7, where the equivalence point for a strong base is right exactly at 7. Now, the weaker the acid, the more pronounced those changes are. So the strong acid is this one here, and then these are each subsequently weaker acids. So if the weak acid is weak enough, it's almost like you don't get a titration curve at all. It's really hard to find the inflection point there. So let's look at the areas of the titration curve for a weak acid and a strong base. We're going to start at the beginning before we've added any base, and we just have weak acid in water. So that's this point here. The pH is just going to be determined by the hydrogen ion concentration, but we can't say that the hydrogen ion concentration is exactly equal to the weak acid concentration because it's a weak acid and it doesn't totally dissociate. So if we're trying to find the pH, we need to know the Ka of the acid so that we can determine the hydrogen ion concentration and then find the pH. After we've left that initial point and we're in the space between that initial point and where the inflection point happens, at that point we have weak acid, but we've added some strong base, and that strong base has reacted with the weak acid to make some of its conjugate base. And anytime you have a mixture of a weak acid and its conjugate base, you have a buffer. And buffer calculations, the pH of a buffer, can be found by using the Henderson-Hasselbalch equation. Later on in this lecture, you'll see that abbreviated HH. And we're going to do a little stoichiometry to find the concentration of the conjugate base and the concentration of the weak acid that's left over, and then we'll be able to find the pH in this kind of what we call a buffer region. When we get out of that buffer region, we've gotten to the place where all of the weak acid has been neutralized by the amount of strong base that we've added. So at that point, that's the point that we call the equivalence point, and the pH is determined by what the products are. So when our weak acid has been totally neutralized by our strong base, it's made the conjugate base. At the equivalence point, these two things have neutralized each other completely. So the only thing that's left over is the conjugate base, and the pH is going to be based on the concentration of that conjugate base and how it reacts with the water around it. So if this is the conjugate base, the pH is governed by this reaction. And to find the concentrations of the products, and therefore find the concentration of the hydrogen ions and find the pH, we'll have to know the Kb of the conjugate base. Now, after the equivalence point, when we've added excess of the strong base, and I'm just using sodium hydroxide there, but it could be any of our strong bases. When we've added excess of our strong base, the pH is just going to be based on the leftover hydroxide ion in solution, and so that's going to be a lot like what we did before. So let's do an example of a weak acid and a strong base. We're going to have similar concentrations here. We're going to start with 50 milliliters of a 0.5 molar benzoic acid, so that's our weak acid. And we're going to titrate it with the 0.1 molar KOH, so that's our strong base. We're going to start off this calculation very similarly than we did our strong acid and strong base. What I want to do is I want to look at each one of these volumes and figure out which one of these is the equivalence point, what's before the equivalence point, and what's after the equivalence point. Now what's nice about this example is the volumes and the molarities are the same as our strong acid and our strong base. So I'm not going to redo all those calculations. I'm just going to use the calculations that we did from our first example. And what we found out was that 15 milliliters was before the equivalence point, 25 milliliters was the equivalence point, and 35 milliliters would then be after the equivalence point. At our first point, we don't have any potassium hydroxide added yet, and so the only thing that we have in our titration flask is the benzoic acid we're starting with. And so the pH is going to be based on the concentration of that benzoic acid, but we need to do an ice table and use the equilibrium expression to be able to find out what the concentration of hydrogen ions is. So to set up that ice table, I'm going to abbreviate benzoic acid just BA. Okay, so I have some benzoic acid and there's water in the flask. It's going to make the conjugate base and some hydronium ions. I'm going to put in it my initial concentration is 0.0500 molarity. I haven't made any of those yet. I don't know how much is going to dissociate, so I'm going to be using X's to symbolize that. And that means at equilibrium, I would get plus X and plus X. And the Ka is equal to the products divided by the reactants. Now to be able to solve for X, which is my hydronium ion concentration there, and that's equal to hydrogen ion concentration, to be able to solve for X, I need to know what the Ka is. And in the problem, it told me that the pKa was equal to 4.20. And so I can use that to find the Ka. I would do 10 to the minus 4.20. And so the Ka is equal to 6.309 times 10 to the negative fifth. Now when I put that into my expression over here, you might realize that unless we can get rid of this minus x, we're going to have a quadratic. And how we could get rid of that minus x is if we could say that minus x was small compared to the initial concentration, then we would say that it was insignificant. And how we judge that is we say that if the Ka, which is a judge of how much it dissociates, if the Ka is less than 1,000 times the initial concentration, that plus or minus x is insignificant. But when we do that, when we multiply this by 1,000, we get 0.06, which is actually higher than our initial concentration. So we can't make that assumption that plus x or minus x is insignificant here, which means that we're actually going to have to do a quadratic equation to solve for x. So remember, when you're solving for a quadratic equation, you would put it in the form of a quadratic equation. So I rearranged it here. All right, and I'll save us some trouble. I used the quadratic equation and I got that x was equal to 0.00174. So that x is equal to our hydronium ion concentration, and we know that pH is equal to the negative log of that concentration. That's the same thing as hydrogen ions in solution. And so when I did that, I got that the pH was 2.759. So after we've gotten past that initial value and we actually start adding our KOH, our second point was adding 15 milliliters of the 0.1 molar KOH. This is kind of our region 2, which for a weak acid strong base is a buffer region. And the steps to do this calculation is we're first going to use some stoichiometry to figure out how much of the conjugate base we've made. And so we'll have a mixture of some acid left over and its conjugate base. And then we're going to use the Henderson-Hasselbalch equation to look at finding the pH of that buffer. So we're going to use stoichiometry or a table to find equilibrium values. And then we're going to put that into the Henderson-Hasselbalch equation to find the pH of our buffer. So when I say a table, what I really mean is something that maybe looks like an ice table, but it's really just to do stoichiometry. I know that my benzoic acid is going to react with my KOH to make water and the conjugate base. Now initially, I have a certain amount of benzoic acid and KOH, and they haven't made any of this. And we actually did a calculation to find out how many moles 50 milliliters of a 0.05 molar solution was, and it was 0.0025 moles. And in our previous example, we figured out how many moles 15 milliliters of a 0.1 molar KOH solution is. If that doesn't ring a bell, the calculation looks something like this. Okay, so that's how we figured out what our initial values were. Now we haven't made any of this yet because it's the initial values, they haven't started reacting. But when they start reacting, one of these is going to be the limiting reagent. Whichever is less is the one that's going to be totally used up. And that's our KOH in this case. So I'm going to subtract that from each one. And I'm going to add it to this side. Now these all react in a 1-to-1 ratio, so that's how I can do them equal on each side. And so now when I do the subtraction, I get 0.001. I get none of this left. I make some water, but I don't really care about that. What I care about is this conjugate base. So the two concentrations, or the two amounts that I care about, are the weak acid that's left over and its conjugate base. So the Henderson-Hasselbalch equation says that the pH is equal to the pKa, which was given in our problem here, plus the log of the conjugate base over the weak acid. And I know I've written HA there, that's just a really generic term for a weak acid. Our weak acid is benzoic acid, and we're just been abbreviating that BA. So when we put these numbers in, the pKa for our acid was 4.20 plus the log of 0.0015, so that's the conjugate base, and 0.0010. That's our weak acid left over. And the pH is equal to 4.376. Now it makes sense that the pH has increased from the last calculation we did, which was the initial pH, but it hasn't increased that much because it's a buffer region, and buffer regions resist change in pH, so we aren't expecting it to jump up a lot here. And just a little pause before we do our next calculation. We calculated the pH when 0 milliliters had been added, and we calculated the pH when 15 milliliters had been added, and the next one that we would do, it was in our problem, was 25 milliliters added. Now here, 25 milliliters added, that was what we calculated as the equivalence point, and this is in the buffer region. And I just wanted to point out that there is kind of a special place that happens in the buffer region that didn't apply to our problem, but it might apply to other problems. That special region in the that special place in the buffer region is at the half equivalence point. At the half equivalence point, the amount of acid left over is half, and so half of it has made the weak conjugate base, and the weak acid and its conjugate base are in a 1-to-1 ratio with each other, which for the Henderson-Hasselbalch equation means that the concentrations are equal and the pH is going to equal the pKa. Now in our problem, the half equivalence point would have been half of 25, which was 12.5. That would have been somewhere in here. Now our problem didn't ask us to calculate the pH there, but if it had, and we knew that at the half equivalence point the pH is equal to the pKa, if our problem had asked for the pH at 12.5 milliliters, we would have known that it was equal to the pKa, and the pH would have been 4.20 in that spot. Our problem asked us to calculate it at 15, which was beyond that point, so we weren't able to use that kind of shortcut. So the next one that we want to do is calculating the pH at the equivalence point. So at the equivalence point, all of the weak acid has been neutralized by the strong base, and it's formed weak conjugate base. So all we have left now is a solution of that weak base in water. When a weak base is in water, it reacts with water to make the conjugate acid. So it's kind of backtracking. It's making a little bit more of that weak acid and some hydroxide ions. Now, out of those two products, a weak acid or a strong base, the weak acid is really not going to change the pH very much, but the concentration of the strong base is going to change the concentration. So we're going to do an ice table to figure out how much strong base we've made, and then we can use the hydroxide ion concentration to find the hydrogen ion concentration and find the pH from there. Now this is going to look a little like two ice tables, but it's really just some stoichiometry and then an ice table. So here we have our benzoic acid and the potassium hydroxide making the conjugate base in water. And this is kind of our stoichiometry. We calculated before that that's 0.0025 moles, and because it's the equivalence point, they are in a 1-to-1 ratio with each other. Now, like I mentioned before, one of these is the limiting reagent. In this case, they are both equal to each other, and so they're going to be totally used, neutralized by the other one. So we're going to have none of this left, and we're going to have 0.0025 moles of the conjugate base made. Now I'm going to take that information and I'm going to do an ice table with that conjugate base that's left over. So this is the conjugate base. It's now reacting with the water to make HA, which in our case is really benzoic acid, plus hydroxide. I know that the initial amount is 0.0025. Some of it is going to dissociate or react with the water to go to this side. And I want to pause there for a second because I want to make sure that I don't forget about something. This is the amount of moles. But eventually what I want to do is I want to find a concentration of my hydroxide. So that's the amount of moles, but it doesn't take into consideration how the volume has changed. So what I should really do there is I should do this in concentration. Moles divided by liters. The liters is our 25 milliliters of hydroxide plus the 50 milliliters of the benzoic acid. So that's 75 milliliters. And so that's 0.075 liters. So when I do this, my concentration here is 0.033 minus x. This is plus x, and this is plus x. And that 0.33 is just the 0.0025 divided by the 75 milliliters. Now this is a reaction for a base, so we're going to set this equal to the Kb. It's going to be the products divided by the reactants. And to be able to solve that, we need to know what the Kb is. Now the problem didn't specifically give us the Kb, but it did give us the pKa, which is 4.20. We used that to find the Ka, which was 6.309 times 10 to the negative fifth. And we know that the Kw is equal to the Ka times the Kb. So the Kw divided by the Ka is equal to the Kb. 1 times 10 to the negative 14 divided by 6.309 is 1.58 times 10 to the negative 10. So 1.5 times 10, so 1.58 times 10 to the negative 10 is equal to x squared. And just like in our last titration curve, if we can get rid of this minus x, it means that we don't have to do a quadratic. How we judge that is if the k is less than 1,000th of the initial concentration, and that's actually true for this situation. If you multiply this by 1,000, you still get less than this. So we can essentially say that plus x and minus x are inconsequential, and that means it's a lot easier to solve. So when I solved for x here, I got 2.28 times 10 to the minus 6. Now what X represents in our situation is the hydroxide ion. So if we take the negative log of that, we would get the POH. And I got that the POH was 5.64. We can then use that to find the pH. We just subtract the POH from 14 and we'd get 8.35. That number matches what we said would happen for a weak acid being titrated with a strong base. We said that at the equivalence point, the pH would be higher than 7, so that checks out. So now that we have finished our calculation at the equivalence point, we can go on to our last point. Our last point was when we've added excess potassium hydroxide, so we went 10 milliliters past the equivalence point, and past the equivalence point, the POH is determined by the excess hydroxide, and then we can use that POH to find the pH. All right, so to find how much excess hydroxide we have, we're just going to set up a little table like we have been. And that's our benzoic acid. We have our initial. We know that we started off with 0.0025 benzoic acid. To figure out how much KOH we need to add, or that we added, we're doing that, a similar calculation. We added 35 milliliters. It's a 0.1 molar. That's 0.0035 moles. Like that. All right, so we subtract out the limiting reagent, which is the lower of them. This, we get 0 here, 0.0010 here. Now we can see that when this reaction has happened and there's leftover hydroxide, there's this leftover hydroxide, but it's also made some of the conjugate base. Both of these things are going to go to raise the pH, but the conjugate base is much weaker than the strong base that's left over. So it's not that this thing doesn't exist, it's that this really has very little impact on the pH compared to having some excess strong hydroxide, some strong base left in there. So when we're calculating the pH, or the POH, the POH is going to be the negative log of the hydroxide ion concentration. We're just going to use this hydroxide concentration in there. If we were to go through the calculations and we were to add this hydroxide in there and then use this as a base, figure out how much hydroxide it makes when it reacts with water, and add that in there, we would see that the amount that the pH goes up accommodating for this isn't much at all. And so the approximation that just the hydroxide is good enough to calculate the POH is going to work for us. So the POH is going to be the negative log of 0.001. That's a POH of 3. The POH and the pH add up to be 14, so 14 minus 3 is the pH, 11 is the pH. All right, now overall, I just kind of wanted to make our own titration curve. And what I've done is on the pH axis, I've written in each of the pHs that we've calculated using each of our points. And on the bottom, I have put in the volumes of KOH. Okay. So we started off at 0 amount added and 2.59 pH. So that was our initial point. Then it went up to about a pH of 4 in our buffer region after we had added 15 milliliters. By the time we had added 25 milliliters, we were up to pH 8. And then at 35 milliliters, we were at about pH 11. Now overall, again, this makes sense. The pH is going up as we add our strong base. And it also makes sense that the pH didn't change much during the buffer region, but then made its biggest change about the equivalence point. I also wanted to talk about a weak base with a strong acid. I'm not going to do a calculation here because the calculations are very similar to the calculation we just did with a weak acid and a strong base. But there are the exact same points along a weak base, strong acid titration curve. The first point is before the acid is added, and there's just a weak base reaction. So that weak base reaction is the base reacting with the water in the titration flask. It's governed by the Kb of that weak base. So just like we did for our weak acid, we would use an equilibrium expression. The Kb is equal to, and we would have something like x squared over the initial concentration minus x. Sometimes we call that initial concentration when we've been doing our calculations. We call it F. There. We would use that to solve for x. X would be equal to the hydroxide ion concentration. We would find the POH, and then we would find the pH from there. Now, because it's a basic solution, it would start off at a high pH. So with no acid added, we would start off at a higher pH than 7. Once we actually start adding some acid, but we haven't gotten to the equivalence point, we are in the buffer region. And we're in a buffer region because we're taking some base, we're adding something like a strong acid like HCl. It's making the conjugate acid. And that mixture of a base and its conjugate acid is a buffer. So we can use the Henderson-Hasselbalch equation to calculate the pH for that buffer region. The buffer region, again, is between the initial point and the equivalence point, so anywhere in between those two. So if we're following along on our titration curve, in this buffer region, once we start adding acid, the pH should start going down, but not very fast. So that's the buffer region. Once we've gotten to our equivalence point, all the base has been converted to acid, and at that point, the pH is just determined by the Ka, and the Ka is for the acid that we're producing, so the conjugate acid. Now remember, when we want to do this, we're going to do some stoichiometry, an ice table. And then we would use an equilibrium expression, and we would use the Ka to find the pH. When we did that, we would find that the pH had dropped drastically because all we have is we don't have any more base left in solution, we just have a weak acid, and so the pH should go down. After we were past the equivalence point and we have excess strong acid, so if we keep on adding acid past the equivalence point, at that point the pH is just determined by the concentration of the strong acid, which is kind of convenient because it's a quick calculation, because all you do is you find, you can use like a table or stoichiometry to find the excess strong acid. And then you can just say that the pH is equal to the negative log of that acid concentration, since it's a strong acid and it completely dissociates. So that's how you can calculate the pH of a titration at kind of any given point along the titration curve. But if you're looking at things from another point of view, if you actually measure the pH for different amounts of the titrant added, you could make your own titration curve, and you can use that titration curve, so something like this, where somebody measured the pH for the volume added, and you can use that titration curve to find the pH at the endpoint, so you could use that information to find concentration of your weak acid or your weak base, whatever you're titrating, or you could use those pHs to find the pKa. And if that's the goal of your titration curve or your titration, sometimes it can be hard, like in a titration curve like this, it can be hard to figure out exactly where the slope is changing the fastest. So that's called the inflection point, and that's how we would help find our equivalence points. Now, if that's the case in your titration curve and those inflection points aren't very clear, you can calculate the first or second derivative to make them more clear. The first and second derivatives are, let's just go for the first one. A derivative is just the change in one thing compared to the change in another. And for us, it's going to be the change in pH divided by the change in volume of titrant added. So you look at the difference between there, that's the change in pH. The difference between these two, that's the change in volume. And so that, what you're doing is calculating the first derivative. Now, if you plot that derivative, if you plot this number versus the amount of volume added, you would get a curve or a kind of a graph that looks like this. And what we're seeing in this graph is that the amount of pH change isn't very much per change in volume until you get to the inflection points, and then it changes a lot. So where the pH is changing the most for the amount of volume added, that is where the inflection points are. And so those can really pinpoint the peak here should be the 2 inflection points. Sometimes if your data is choppy enough, a curve wouldn't look like this. It would look like this. And so it's hard to know, is that the top? Is that the top? Is that the top? The top? So sometimes it's hard to tell. So if something like that happens to your first derivative, you can go ahead and calculate the second derivative. And the second derivative will have a peak up and then a peak down like this. And where it hits 0, that is the inflection point. So where it hits the 0, that's the inflection point. So sometimes the first derivative is easy enough to identify those inflection points. Sometimes the second derivative is a little bit more clear. So in this video, we talked about 3 different types of titration curves. We talked about strong acid and strong base. We talked about titrating a weak acid with a strong base, and we talked about titrating a weak base with a strong acid. And we talked about the regions of each one of those titration curves, kind of the general shape and what is special about each region. And we talked about how to calculate the pH for different volumes added for each one of those types of titrations. At the end, we talked about how to use the derivative to find equivalence points if they're not clear in your titration curve.